We've gone pretty far without discussing one of the main applications of linear algebra, solving systems of linear equations. And in this lecture, we'll learn how to think about solutions to systems of linear equations, both geometrically and algebraically. A linear equation in the variables x1 through xn is an equation of the form a1x1 plus a2x2 plus ... an xn equals b, where the a sub i's are real coefficients and b is a constant. Said another way, it's an equation where some linear combination of variables is set equal to a constant. Let's look at some examples. The equation 3x plus 2y minus 7z equals 5 is a linear equation in the variables x, y, and z because I have a linear combination of x, y, and z set equal to a constant. Linear equations have the property that each of the variables appears only to the first power and are multiplied by a constant. Nonlinear equations, on the other hand, will have a strange dependence on at least one of the variables. For instance, 3x minus 2yz equals 4 is not linear because the y and z are multiplied together. X squared plus y squared plus z squared equals 25 is also not a linear equation because the left side depends on the squares of the variables. Linear equations can, because of their form, always be represented by setting a dot product of some vector, a1 through an, with a vector of variables, x1 through xn, equal to a constant. If you like, we can also represent it as a matrix product of a single row of constants times a single column of variables. One of the things we have seen in earlier lectures is the set of vectors x, y, z that satisfy this linear equation, 3x plus 2y minus 7z equals 5, will be a plane in R3. You may also recall that 3x plus 2y equals 5 has a solution set that looks like a line in R2. This will be a general feature of a linear equation in n variables. The set of all points in Rn that satisfies the linear equation will be a linear object we call an n-1 dimensional hyperplane. A hyperplane is just a fancy name for a generalization of a plane. A point is a zero-dimensional plane, hyperplane. A line is a one-dimensional hyperplane. A plane is a two-dimensional hyperplane. The point is that linear equations have very nice solution sets that, as the name implies, are also very linear, flat objects. Contrast that with the nonlinear equation, x squared plus y squared plus z squared equals 25. You may remember that is an equation of a sphere. When we say that, what we mean is the set of all points that satisfy this equation will form a surface in R3 that looks like a sphere. This solution set is not a hyperplane. Now, a system of linear equations is just a collection of more than one linear equation. For instance, this is a system of linear equations. Linear equations arise very naturally in problems where you're demanding that some linear combination of things satisfy some constraint. For instance, suppose you say, how many quarters and nickels do I need to make $1? Then you get a linear equation. If q is the number of quarters and n is the number of nickels, then by counting cents, you get this relationship. Q times 25 plus n times 5 equals 100 cents. That's a linear equation in the variables q and n. In this case, you're hoping to find whole number solutions if you want the answer to make sense. No pun intended. In economics, a linear equation might arise from a budget constraint. If you have a combination of objects and you have only a certain number of dollars to spend on them, that gives a linear equation. If x sub I represents the quantity of item I and a sub I represents the cost for that item, then this linear equation says that the total cost to purchase all the items is b. Another example which we explored earlier, was taking a linear combination of nuts and chocolates and asking them to satisfy some nutritional constraints, like a certain number of fats, carbs, and proteins. If the number of nuts and chocolates are unknown variables, that gives a system of 3 linear equations. One a constraint for fat calories, another for carbs, and another for proteins. A system of linear equations naturally arises when you're trying to balance a chemical equation. What balancing means is figuring out how much of various substances you need to produce a chemical reaction. For instance, ethane combines with oxygen when you burn it to produce carbon dioxide and water, steam. How much of each are involved in a reaction? Well, what we want is to balance this equation. C2H6, which is ethane, plus O2, oxygen, gives CO2, carbon dioxide, together with H2O, which is water. If you haven't seen the chemical notation before, the letters C, H, and O represent atoms of carbon, hydrogen, and oxygen. The groupings represent molecules of various substances, and the subscripts tell you how many atoms are involved in each molecule. To balance this equation means what amounts of each molecule are needed to make the elements involved on both sides equal. That's what we mean by balance. To that end, let W, X, Y, and Z represent unknown amounts of each molecule in this equation. So, when we look at it this way, what we're saying is W molecules of ethane plus X molecules of oxygen should combine to give Y molecules of CO2 plus Z molecules of water. To find W, X, Y, and Z, notice that for each of carbon, hydrogen, and oxygen, we're going to get an equation that balances those elements on both sides. For instance, since I know that the number of carbon atoms on both sides must be the same, I'm going to get the equation 2W equals Y. Looking at hydrogen and realizing the number of atoms on both sides is the same, we get 6W equals 2Z. Finally, for oxygen, we see that 2X equals 2Y plus Z. So if I put all the variables on one side, I get these equations. 2W minus y equals 0, 6w minus 2z equals 0, 2x minus 2y minus z equals 0. These are 3 linear equations. If you think about it, balancing any chemical reaction will result in linear equations like these because all you are ever doing is taking linear combinations of various atoms on both sides and setting them equal. Let's look at one more example from the domain of physics. Linear equations often arise from the study of electrical networks. Don't worry if you've never studied electrical networks, just observe what kind of mathematical relations there are. The basic idea in an electrical network is you have electrons moving around. You may have a battery that's providing a kind of electrical force to push the electrons around. This is called voltage. You have something called current, which is like the flow of electrons through a wire. And you have things called resistors that are powered by the battery when current flows through them. Just think of lights if you wish. The resistors, in some sense, use up the voltage. This is called a voltage drop. And exactly how much is given by something called Ohm's law. Ohm's law says the voltage drop across a resistor is equal to the current times the resistance. If V stands for voltage, and I for current, and R for resistance, then the equation is V equals I times R. So the voltage drop is proportional to the current, and the resistance is the proportionality constant. It's very similar to another equation you might be familiar with, that frictional force is proportional to velocity, with the frictional constant as the proportionality constant. There's another law called Kirchhoff's voltage law that says that the total voltage drop around any closed loop is equal to the voltage provided by the batteries. That holds true even in a more complicated electrical circuit like this. There is one more law called Kirchhoff's current law that says that at any node where branching occurs, the sum of the currents going in equals the sum of the currents going out. So in this diagram, if you know the resistances but you want to find the currents, I1, I2, I3, then Ohm's law tells you the voltage drops across resistors have a linear relationship to the currents through them. And both of Kirchhoff's laws give you the linear equations. In our diagram, we get some equations like this. I1 minus I2 minus I3 equals 0. Twice I1 plus 3 times I2 equals 8. Twice I1 plus 5 times I3 equals 8. Note how these are all linear equations. All right, so we've seen several examples now of how linear equations can arise, and we will see many more examples in the lectures to come. Now let's see how we might try to solve such a system. Suppose we have this system of equations. To solve this system means find all sets of numbers, x1, x2, x3, that satisfy all three equations simultaneously. In other words, find a point x1, x2, x3 in R3 that makes all equations true simultaneously. Another way to say it is, find a vector x1, x2, x3 that satisfies this matrix equation. For instance, x1 equals 3 and x2 equals 1 and x3 equals 0 will work. Are there any other solutions? Now, before we try to answer this question algebraically, let me show you how our geometric insights will give us some perspective. I know the set of all solutions that satisfy each single equation is a plane. So the set of all solutions that satisfy all equations simultaneously must be the intersection of all the planes represented by each equation. What can the intersection of three planes look like? Well, generically speaking, the intersection of two planes is usually a line. And if you intersect that with another plane, you will usually get a single point. So generically speaking, you expect to get a single solution vector to this set of equations. However, there are degenerate cases. If all three planes happen to be identical, then the intersection will be that entire plane. You'll get a whole plane of solutions. That's infinitely many solutions. Every point in that plane will satisfy all three equations. But if two of the planes from these three equations are identical, the third plane may cut this plane in a line. So in that case, you'll get a whole line of solutions. And if two of the planes are parallel and not identical, then there will not be a point that satisfies both planes simultaneously. So even when you intersect these planes with another plane, the set of solutions to all three equations is going to be empty. So notice that without doing a lick of algebra, we already see that a system of solutions will either be empty, a single solution, or infinitely many solutions. In fact, by reasoning about hyperplanes in a similar fashion, you will see this is a general feature of any system of linear equations. It'll either have one solution, no solution, or infinitely many solutions. And you can see this just from thinking about the geometry. All right, now how do we actually find the solutions algebraically? Let's take a look at this system again. When we solve such a system of equations by hand, it is tempting to just make some arbitrary choices for substitutions until we get an answer. But how can we solve a system of equations like this in a systematic way? The problem with doing this on a case-by-case basis is that we get no insight into what is going on. In addition, we'll want something that'll work for a system of 3 equations or 300 equations, something we could program a computer to do. In practical applications, such as airline scheduling problems, you might have an even larger system of equations you're trying to solve. We're going to discuss a method of solving systems of linear equations systematically, called Gaussian elimination. Although this method is named after the 19th century mathematician Carl Gauss, It dates back to the Chinese in the 3rd century BC, and it probably has been rediscovered many times over the centuries. The idea is simple. Let's convert the system of equations into an equivalent system of equations, and by that we mean a new system of equations that has exactly the same solutions as the original. Let's first recall a few basic facts about equations. I can add one equation to another equation to get a third true statement. So, if A equals B and C equals D, then A plus C should equal B plus D. Also, if I do the same thing to both sides of an equation, the statement is still true. So if A equals B, then A times C equals B times C, no matter what C is. So now coming back to our system of equations, if I take one equation and multiply it by a non-zero constant, that will not change the set of solutions to the system. So if I change the first equation to 2x1 plus 2x2 plus 2x3 equals 8, the set of solutions to all three equations would stay the same. Any solution that worked for the original system will still work for the new system. Any solution that works for the new system will still work for the original. However, if I had multiplied one equation by 0 on both sides, then that equation becomes 0 equals 0, which is true, but now I've lost a constraint that the variables must satisfy, and I've possibly enlarged the set of solutions. So multiplying by 0 is prohibited if we want to be sure our solution set is unchanged. Another operation I'm allowed to do is to add a multiple of one equation to another. The multiple could be positive or negative. That won't change the set of solutions either. So, for instance, if I take the second equation and add minus 2 times the first equation, that will have the effect of canceling the x1 term, and it produces a second term of 5x2 minus 2x2, which is 3x2. And similarly, you get a third term of minus x3 minus 2x3 equals minus 3x3. And for the constant on the right side, you get 11 minus 2 times 4 equals 3. So the second equation becomes 3x2 minus 3x3 equals 3. This system has the same set of solutions as the original. The way to see that is anything that is satisfied by the original system now still satisfies this one. But we know we didn't enlarge the set of solutions because this step is reversible. If I want to get back to the original system, all I need to do is to add twice the first equation to the second, because I subtracted twice the first equation earlier. So anything that satisfies the new system still satisfies the old. Notice how unwieldy it is to keep rewriting all of these variables. We're going to use shorthand now to represent a system of equations. So this gets replaced by this. This is called an augmented matrix for the original linear system. The augmented part is the rightmost column, which we separated by a vertical line to help us remember that these come from the constants in the linear equation. Remember, this augmented matrix is just a shorthand for a system of linear equations. It just shows me the coefficients rather than writing out all the variables. If an equation doesn't have a variable, I can think of the variable as having the coefficient 0. Like our third equation had no x2, so we have a 0 in the third row in the x2 position. Now, performing operations that don't change the solutions can be represented by what are called row operations on the augmented matrix. For instance, if I want to subtract 2 times the first row from the second row, I can represent it this way. The notation R2 minus 2R1 just tells me what I did. I'm going to keep doing things that won't change the set of solutions. For instance, I could next try to make the minus 1 in the bottom left corner into a 0. This would correspond to eliminating the x1 term in that equation, and I could do that by adding the first row to the third row. So minus 1 plus 1 equals 0, 0 plus 1 equals 1, 2 plus 1 equals 3, and minus 3 plus 4 equals 1. I'll get this. Now we could just keep going, playing this game, always getting an equivalent system with the same solutions, but where are we headed? I'll confess, I have a little strategy that I haven't told you yet. You see, where I'm trying to go is to an augmented matrix that looks like this, where I have just a single one in each row and column. I claim the corresponding system of equations has a very obvious solution. If the right-hand side is a bunch of constants a, b, c, then this augmented matrix would be saying x1 equals a, x2 equals b, and x3 equals c. In other words, it would be telling me the solution to the system of equations. I can recognize this pattern because I will see all zeros on the left side except for a diagonal of ones. And you've seen this pattern before. It's called the identity matrix. And the diagonal has a special name. It's called the main diagonal of that square. Now, by doing row operations, I may not be able to get to this pattern, but I'm going to try. So in my original augmented matrix, my strategy is to try to make zeros in all these places, and I'll do it in the following order. I've been trying to zero out the entries below the main diagonal first, working column by column from left to right. Then I will work above the main diagonal to turn all those entries into zeros, and generally it will be easier at that point to work from right to left. Let's return to our example. You see here that I had zeroed out the first column except for a 1 at the top. Now look at the second column. Since I realize I want to have a 1 in the main diagonal, I'm going to do another thing that won't change the set of solutions. I will swap the rows. Now why is that allowed? Well, it clearly won't change the set of solutions because it is just expressing the same equations but in a different order. And some might wonder whether the order of the rows has anything to do with the order of the variables corresponding to the columns. And the answer is no. Swapping rows does not change anything about which variables are related to the columns. So swapping rows is just a move I want to use to help me get ones on the main diagonal. Swapping rows 2 and 3 gives me this. Now, I can get a 0 on the bottom of the second column by subtracting 3 times the second row. Notice how this doesn't mess up the work I did to zero out the first column because both row 2 and row 3 had zeros there. So then I'll get this. Now, I can multiply the third row to get this. Now, do you see that because I have 0, 0, 1 in the last row, that it will be easy to zero out the entries in the third column by subtracting multiples of the last row? Doing this won't affect the other columns because 0, 0, 1 has zeros in those columns. So I'll get this. Finally, we'll do a last step, which shows me the solution to this system, as well as the original system of equations, is x1 equals 3, x2 equals 1, and x3 equals 0. So the vector 3, 1, 0 is a solution. And in fact, we showed it is the only solution to the original system of equations. You can check that it works too. Let's summarize what operations we used. We basically used 3 operations on the rows of the augmented matrix. We swapped rows, we multiplied rows by a non-zero constant, and we added a multiple of one row, j, to another row, I, and replaced row I. These operations are called elementary row operations, and they do not change the solution to a system of linear equations. The process of getting from a configuration to an ideal configuration is called row reduction, or Gaussian elimination. Now, I encourage you to pause and assemble a set of questions that you might have about this procedure. And then after the pause, see if I answer them. One question you might have is, what if you can't for some reason get the method to produce the identity matrix on the left side of the augmented matrix? Under what conditions will the method fail? We've already seen that a system always has either no solution, one solution, or infinitely many solutions. Producing an identity matrix on the left side is equivalent to finding a unique solution to our problem. There must be other situations that will lead us to find no solution or infinitely many solutions. So here's one bad thing that could happen when you try to do row reduction. You might end up with a row that looks something like this. A row of zeros on one side, and on the other side, a non-zero number like 8. If you get a row like this, it stands for the equation 0x1 plus 0x2 plus 0x3 equals 8, which is a nonsensical equation because 0 can't equal 8. So this will be a system of equations that has no solution. Now, if you get a row of all zeros, including the augmented part on the right side, like this, 0, 0, 0, together with a 0 on the right side, that is not going to be a problem. That just means you had an equation that was redundant. It was already a linear combination of the other equations, and row reduction just eliminated that equation. So if you get something like this, this would represent the system of equations x1 plus 3x3 equals 1, x2 plus x3 equals 2. And what you find is that you can choose the x3 to be anything you want. Once you do that, x1 and x2 are determined. We then say you can choose x3 freely, or we say x3 is a free variable. If you have a free variable, then there's going to be infinitely many solutions. There are a lot more questions to consider. For instance, the left side of the augmented matrix may not even be a square matrix if it has a different number of equations than unknowns. What augmented matrix should I be aiming for then? Another question you might ask is, what happens if I use a different sequence of row operations? How does that affect what solutions I get? We'll have to address these questions in the next lecture. But the thing to keep in mind here is that even though row reduction may seem rather tedious, the method is very important because it gives us insight into the structure of solutions. It reveals hidden structure that we didn't see before, one of the themes of linear algebra that we mentioned at the start of the course.